Two frameworks dominate production LLM serving today. Same hardware, same models, wildly different results depending on your workload. SGLang versus VLLM. Here's how to choose. Both VLLM and SGLang exist to solve the same fundamental bottleneck. When an LLM generates tokens, it builds a KV cache, key and value matrices that grow with every token produced. At 4,000 tokens, that cache consumes over a gigabyte of GPU memory per request. On an 80 gigabyte A100, this limits you to a handful of concurrent long context requests. Traditional frameworks made this worse. KV cache memory was allocated upfront, contiguously, at maximum sequence length from the moment a request started. A request that generates 300 tokens out of a possible 2,000 claims 2,000 tokens worth of memory. 84% wasted. New request queue behind it, starved for memory that isn't actually being used. Both frameworks solve this, but they focus on different parts of the problem, and the right choice depends entirely on your workload. VLLM's answer is PagedAttention from UC Berkeley in 2023. The insight: borrow the solution operating systems use for process memory. Instead of one contiguous KV cache block per request, split it into fixed-size pages, 16 tokens each. A block table maps each request's logical positions to physical pages wherever they happen to be free in GPU memory. Non-contiguous, no pre-allocation. When a request finishes, its pages are immediately freed for the next request. Memory fragmentation drops to under 4%. The result: VLLM can serve dramatically more concurrent requests on the same GPU. In the original benchmarks, VLLM achieved up to 24 times the throughput of Hugging Face TGI, not by running faster per token, but by wasting almost none of the available GPU memory. VLLM's strength is breadth. It handles diverse workloads efficiently regardless of sequence length distribution or request pattern. If your requests are unpredictable, varied, with no dominant shared prefix, PagedAttention is exactly the right tool. SGLang asks a different question. Why are we computing the same KV cache entries for the same tokens, over and over, across every request? Consider a production chatbot. Every request starts with the same 400-token system prompt: company context, persona, safety guidelines. In a standard setup, every request runs a full prefill over those 400 tokens. For 10,000 daily users, that's 4 million identical prefill operations. Pure wasted GPU cycles. SGLang's RadixAttention eliminates this. It organizes the KV cache as a radix tree. The system prompt lives at the root, computed exactly once. Every new request sharing that prefix gets an instant cache hit. Only the user's actual query, the tokens that differ, ever touches the GPU for prefill. The tree handles complex sharing too. Agent contexts, multi-turn conversations, shared chain-of-thought prefixes all benefit from the same structure. Hot prefixes stay resident via LRU eviction, cold ones are freed. In production deployments with high prefix sharing, cache hit rates between 60 and 90% are typical. That translates to dramatically lower time to first token and significantly higher throughput on the same hardware. For structured output, JSON schemas, function calling, grammar-constrained generation, the two frameworks diverge sharply. VLLM handles this through logit masking. At every decoding step, a grammar engine inspects the partial output, determines valid next tokens, and filters the vocabulary before sampling. This works, but it runs in Python on every single token. For a 32,000 token vocabulary, that's 32,000 checks every step in the Python process. For long structured outputs, the overhead is measurable. SGLang takes a fundamentally different approach. When you provide a JSON schema, SGLang compiles it at startup into a compressed finite state machine. Done once. During decoding, when the FSM determines that multiple consecutive tokens are fully determined, like the fixed key names in a JSON object, it jumps through the entire deterministic span in a single forward pass. 4 guaranteed tokens becomes 1 GPU operation. Schema compiled once. No per-token Python overhead. Constrained decoding becomes nearly free. For agents, function calling pipelines, and any schema-heavy workload, this architectural difference is significant. On throughput, the choice depends entirely on your workload profile. For general, diverse workloads, varied users, varied lengths, no dominant shared prefix, both frameworks are competitive. On an A180GB with Llama 370B at high concurrency, both deliver 17 to 19,000 tokens per second. The gap is within 15%. The picture changes dramatically for prefix-heavy workloads. A chatbot with a 500-token system prompt served to thousands of users. VLLM pre-fills those 500 tokens for every single request. SGLang hits the cache. With a 90% hit rate, SGLang is effectively running pre-fill only on the user's query. Same GPU, 2 to 3 times the effective throughput. For agent workloads, the advantage compounds. Shared context grows with tool call results, and every invocation that reuses prior context saves more compute. The rule of thumb, below 20% shared tokens, both are equivalent. Above 40%, SGLang consistently outperforms. Above 70%, expect 2 times or more throughput on the same hardware. Throughput is aggregate. Latency is what users feel. Time to first token, the delay between sending a request and receiving the first generated token, is dominated by the prefill phase. For VLLM, every request runs full prefill every time. A 500-token system prompt adds 500 tokens of prefill latency to every request, compounded by queuing when prefill competes with ongoing decodes. For SGLang with a cache hit, those tokens aren't prefilled at all. Time to first token drops to the cost of the user's query only. 20 to 100 tokens, not 500. In benchmarks with 90% cache hit rates, SGLang achieves up to 5 times lower time to first token versus VLLM. Time between tokens, the per-token decode latency, is essentially equivalent between the two frameworks. Both use flash attention kernels and continuous batching. P99 tail latency is more consistent in SGLang on prefix-heavy workloads. The variable prefill cost is gone for cached requests, removing the main source of latency spikes. Summary: for latency-sensitive applications with shared prompts, SGLang wins. For raw decode latency, both are equivalent. For large models that don't fit on a single GPU, both frameworks support the standard distributed strategies. Tensor, parallelism, splits layers across GPUs with NCCL all reduced between passes. Pipeline parallelism assigns layer groups to different nodes. Expert parallelism handles mixture of experts models like DeepSeek and Mixtral. VLLM has been running distributed inference at scale since late 2023, with substantial production experience across diverse hardware. SGLang added multi-GPU support in 2024 and has closed the gap considerably, with particularly strong results on DeepSeek models. For most teams on 4 to 8 GPUs, both frameworks are capable. For cutting-edge multi-node at 64 GPUs or more, VLLM's longer production track record is the safer choice today. Both frameworks expose an OpenAI-compatible REST API. Same endpoints, same request format. Switching requires changing one base URL. VLLM has the larger ecosystem, native LangChain and Llama index integrations, Ray serve for auto-scaling, Kubernetes operators from multiple vendors, official Docker images, and seamless Hugging Face hub integration. Over 38,000 GitHub stars. A community that has been battle-testing deployments for 2+ years. SGLang is newer, around 14,000 stars at time of recording, but growing fast. DeepSeek models are particularly well supported. Migration from VLLM to SGLang is straightforward at the API level. Client code changes are minimal. If existing ecosystem integrations drive your decision, VLLM is the safer bet. If you're building a new deployment and your workload fits SGLang's strengths, the ecosystem gap is manageable. Here's the practical decision framework. Use SGLang when your workload has a high shared prefix ratio, chatbots, agents, any deployment where most requests start with the same system prompt. Use SGLang when structured output is core to your application. JSON APIs, function calling, schema-constrained generation. Use SGLang when time to first token drives user experience and your cache hit rate is above 50%. Use SGLang for agent frameworks where contexts accumulate and get reused across multiple invocations. Use VLLM when your workload is diverse and unpredictable. Varied users, varied lengths, no significant shared prefix. Use VLLM when you need the widest ecosystem integration. LangChain, RayServe, Kubernetes, community tooling. Use VLLM for multimodal workloads. Images, audio, video. VLLM's multimodal support covers more model architectures. Use VLLM for large multi-node deployments where production track record matters. The single number that determines your choice. What percentage of your total token budget is shared across requests? Run this analysis on your request logs. Above 40% shared tokens, benchmark SGLang first. Below 40%, VLLM's general-purpose efficiency is hard to beat. When in doubt, both frameworks deploy in under an hour. Benchmark on your actual workload. That number is the only one that matters. VLLM for diversity and ecosystem. SGLang for shared prefixes and structured output. Choose based on your workload, not the hype. This is systems engineering meeting LLMs. Follow for more.